Hello everyone. This is team Qudit Creons, and I'm Abhishek Raj representing this team. So, I'll be walking you through our quantum computing project, where we have re-implemented a variational quantum algorithm to solve linear systemic equations. This project was developed as part of a hackathon, and the goal was to build more efficient and robust solution compared to the original research paper by Carlos Bravo-Prieto. So, moving on. So here in the README description, we have mentioned our title or the overview, the problem description, and the implementation details. Uh, to mention the leads, this has been implemented using Jupyter Notebook and Classiq IDE. So we implemented most of the code on Jupyter Network environment. And for the simulation part, for the job simulation part, we have used the Classiq IDE. So moving on to the actual notebook, we have implemented the algorithm. Okay. So as I have told you earlier that we have used Jupyter Notebook environment and this is the research paper which we have used, Carlos Bravo-Prieto. We have quite a re-implemented the existing algorithm which we are used to asked to do. So here I have installed the Classiq, and before using the Classiq you have to create an account and authenticate it using this command. Now you can also check the version of the Classiq. So before diving into the details of the code, let me give you a bit of context. Linear system of equations are everywhere, whether it's in physics to solve differential equations, in engineering for circuit analysis, or even in data science for regression models. So let's start by explaining the problem we are solving. Essentially, we are trying to solve a system of linear equations of the form Ax equals to 0. Traditional methods like Gaussian elimination can get really slow as the matrix A becomes larger. But by using a variational quantum algorithm, we can potentially find solutions faster by encoding the problem into a quantum state. The first part is variational ansatz. Let's jump into the code. The first and most important part of this project is the variational ansatz, uh, which is essentially a guess for what the solution might look like. And in quantum computing, we create this guess using a parametric quantum socket. So our code defines a main, function main, okay, which acts as the entry point for the ansatz. In this code, you can see that we are allocating two qubits. Uh, we then apply a series of parametric rotation gates like Rx, Ry, and Rz, as well as CZ for gate for entanglement. So these rotation gates are adjusted during the optimization process to minimize the cost function, which help us find the solution to a linear system. And also to mention, the ansatz is flexible, meaning it can adapt to different types of problems by tweaking the parameters. So moving on, to make the process smoother, we have used like the Classiq framework, especially in the simulation part. It was so smooth without worrying about the low level gate problems and abstraction uh, related problems. So with create model, with create model function, we we synthesize to get the actual quantum circuit. This approach makes it easier to design complex circuits, especially when working on variation algorithms like the one we are working with in this algorithm, which we have implemented. So we have used, as I mentioned about, we have used the Classiq ID on the ID itself to do the job simulations. Okay, coming up to the fourth one, analyzing the CX gate count. So one of our key was to improve on the original research paper. We focused on optimizing the ansatz by choosing a more efficient layout of gates, which reduces the overall gate count, especially the number of expensive CX gates. This not only speeds up the execution but also makes the algorithm more scalable. Okay, to sum up, our project demonstrates basically how a variational quantum algorithm can be used to solve linear system equations more efficient by leveraging Classiq frameworks, especially special mentioned in Classiq, making it more flexible and uh, more accessible from different points. We are able to design a flexible and powerful variation ansatz We hope that this work can pave the way for more effective funding algorithms, which may result in tackling problems classical computers struggle with. So thank you for considering this. Thanks again.